Thanks very much. I'm hoping you hear me, and I try to share my screen in order to get into the presentation. I hope it works. Should work. No, one moment. No. Yes, it now should work. I think it's okay. Can you hear me?
Yes. The slides are up. You can continue.
Much. In the lecture just before, we heard a lot about carbon footprint, carbon prices, carbon trading. I will a little bit more focus on the opportunities which arise with decarbonization issues. And I would reflect the interaction between the refinery, between the petrochemical and the chemical areas. I will try to reflect this on a couple of points. First of all, I would give a background, what is the meaning of decarbonization. Then I will reflect on very essential points for the decarbonization, like as carbon capturing, green hydrogen as a carbon-free building block. I will go very short into the thematic of the advanced fuels and chemicals and will lose some words about enhanced process efficiency, and will close with some selected low-carbon technology examples and give an outlook for the next decades, which we are thinking of. If we go to the word decarbonization, there is a lot of keywords. There are many subject areas, but there are also a lot of different interpretations. If we heard synthetic fuels, carbon utilization, green hydrogen, green CO2, green components, there's a lot of interpretation. I will try to make it somewhat clearer here. So if we look at the scientific facts, is that there is greenhouse gases like CH4, CO2 halogens, and the nitrogen oxides. The heart of the issue is that the emission plus the heat from the atmosphere will lead to global warming. If you look at the right side, there is the cake diagram where the global CO2 emissions are listed, and you see that Russia and Germany are at least in the same range for emissions. That a very big global emissions comes from China and from the US. If you try to handle the greenhouse gases from the sources, and if we look only at Europe, you see that the most part of the greenhouse gas emissions comes from the fuel combustion. Everywhere we have a combustion of fuel, we have a lot of emissions. This is without the transport sector, where we always have combustions. Then we have the transport sector, which is a quarter of the greenhouse gas emission, and the remaining part is for agriculture, industries, and waste management. If we focus on the transport sector, which is a quarter of the greenhouse gas emissions, we see that the most part is gains from the passenger cars, and the remaining part which go from the aviation industry, from the shipping and rail industries. If we look at the dilemma between the must to reduce CO2 carbon and the global energy demand, we see that there is a dual challenge, because looking at the graphic in the left picture, we see that within the time from 2016 to 2040, we will have, of course, a decrease of power needed. We will have a decrease for building heating and so on, because we have better buildings. We will also have a decrease for the passenger cars, for the passenger vehicles, but we will have an increase for the road freight because of the increasing transportation sector. We will have an increase of the aviation and shipping industry, and we will also have a significant increase for the petrochemical industry, especially plastics, which will be increased more and more, and a small part for others. If we see that we in total have an increase in energy demand, and if you saw at the right picture, at the same time we have to reduce the carbon intensity or the carbon emissions by more than 90%. If we do nothing, we see the red line in the right picture, we will increase the greenhouse gas emissions, and we have the intention to follow the green line up to 2015. If we try to understand what is the interaction between the refinery, between the petrochemical, and between the chemical area, we can look at this as a simplified slide, but it's always complex enough. If you try to represent the refinery by petroleum processing, which processes the crude oil, and if we try to represent the petrochemical industry by the steam cracking, we see that most of the crude oil which is processed in the refinery will go to the transport sector and others, blending, lubricating waxes, petroleum coke, as well as asphaltenes. And that only a small amount, 15%, will go as intermediate products to the petrochemical. And then, this is the next slide, will go from the petrochemical to the chemical industry in order to produce the building blocks for the value chains. For example, ethylene, propylene, which can carry out all the respective products we have in the chemical. What does it mean? This means that there are a lot of regulations, which we heard about in the lecture just before. So there's a Paris Agreement. I will not reflect in more detail on this. We have some national regulations. We have some further regulations, such as a plastic tax, which come in force this year. And all these regulations works as a kind of driver to decarbonize or to strengthen our efforts for a low carbon industry. As we've seen from the slides before, it seems that the oil and gas processing makes the beginning. But, and that is a very important point, is it no ad hoc replacement feasible? If you look at the left picture here and on this slide, it's a very schematical picture of a refinery with products as fuel gas, LPG, gasoline, also transport fuels, the jet fuel, the diesel fuel, and also the light and heating oils and the residues at petcoke, bitumen, and sulfur. There are, for some of them, some lower, let me say, lower greenhouse gas substitutes, which is derived on the right table here. This means for the transportation fuels, we are able to substitute electrical vehicles. We can use bio-based fuels, e-fuels, which I come later on this topic. For the fuel oils, we can direct use natural gas. For the LPG, for the building blocks, for the chemistry, there are also some substitutes which can replace fossil products. But there are also a lot of components which are not easy to displace or replace by such new greenhouse gas products. In such cases, we have to implement new pathways. We have to implement new interconnections between refinery, petrochemical, and chemical industry. And that is what I want to focus on in the next slides. Decarbonization is, especially speaking, the wrong word, because we are not, or we won't not remove all the carbon. Carbon is needed for the chemical, for the refinery products. It's not going out without carbon. So we have to handle this carbon, and we have to handle this in a way that is sustainable. So which measures we have to decarbonize a refinery or a petrochemical complex or the whole industry? There is no one-fits-all solution. There's a couple of measures which can be applied in combination to reach a significant reduction of carbon intensity. At the left side of this picture, you see these blue circles. This is the measures we have for existing installation, for existing plant. We can increase process efficiency. We can replace green hydrogen in cases where we have an add-on, where we have capacity increase and we can use green hydrogen. We can make a post-treatment in order to remove CO2 from the flue gases, from the off gases, and storage it. We can implement on stricter fuel qualities and specifications. At the right side, we have kind of new pathways which requires new installations and which requires new interlinks between refinery and petrochemical, such using green hydrogen as a building block for the downstream processing. We can not only capture the carbon, but we can also utilize it. We can use it as a feedstock, the carbon feedstock for the further downstream processing. And we can use advanced fuels, biofuels and chemicals, as well as so-called power fuels or power chemicals, so-called PTX fuels, which we can use in order to handle this issue. Carbon capturing CO2. If we talk about CO2, we talk about a property, or we talk about a component which has to be removed. But on the other side, carbon dioxide is a very value compound, and we should not abandon carbon, but we should find right balance between emissions, which is global warming, and things where we can we can use this carbon from the emissions in order to make new products. So with this knowledge in hand, we have the targets for the carbon capture and storage, and we have the target for the carbon capture and utilization. Capturing CO2 can be done from concentrated sources like industrial emissions, flue gases, which can be purified, which is much easier because they have the high concentrations. It's much easier to remove CO2 from such products, from such sources. And we have the direct air capture with this. Much not so easy because we have low concentration and is in any cases very expensive today. But both capturing methods can be used for decarbonization. If you look at the application of CO2, and I'm only focused on the right side where we have the application, the chemical and biological transformation, we see that with the CO2 we can make new products. We can lead to the production of chemicals and materials, and we can use it as feedstock for polymers, for plastics, for organic chemistry, minerals, and at the right side we can use it for the production of synthetic fuels, which is also called designer fuels. But, and that is a very essential point, we have to assess how long the CO2 is restored, how long it is not released back to the atmosphere. If you look at the right diagram there, we see a time schedule where we have the non-permanent storage of CO2, we have the semi-permanent and the permanent storage. And if we look at the synthetic fuels, where we use CO2 as a part of the feedstock for producing synthetic fuels, we see that it's a very short time, because if this synthetic fuel is processed in an engine, a CE engine, we will see that we have a very short releasement back to the atmosphere. If we use polymers or minerals or the concrete making from CO2, is a semi-permanent storage. And if we use it in the storage, underground storage, we have a relatively permanent storage. This is essential if we try to do lifetime analysis here. This should be mentioned in this kind of assessment. Green hydrogen. Talking about hydrogen, hydrogen is a very important component within refinery and petrochemical. You see the industrial sector, refining, chemical, and iron, steel, and other industries, that for the refinery, a quarter, 25%, hydrogen is used for all the hydro treatments, hydro cracking units. For the chemical industry, there's mainly the polymers, ammonia, as well as the production of the resins. And as this is coming more and more for the iron and steel sector, we are able to use hydrogen for the iron production. This would be 10% here in this slide, but this would be much more in the next years. If you look from the sources, the hydrogen sources are mainly coming from the natural gas up to now, then a part of oil and coal, and up to now there's only a very few or very low portion of hydrogen coming from the water electrolysis, which is also will also increase within the next years. Using green hydrogen as a renewable feedstock, we have on this slide the hydrogen route marked with a green color here. You see that we can use hydrogen with electricity and electrolysis in order to make green hydrogen, and together with captured carbon, we can have a feedstock like a syngas in order to have the products coming from them. Hydrogen is classified into main two areas. We have the gray hydrogen. This is a normal or standard hydrogen coming from the steam methane reforming SMR. Then we have the green hydrogen. The green hydrogen is coming from the electrolysis, and we have a lot of options in between, because we can use it as a kind of bridge technology between the gray hydrogen and the green hydrogen. This is the hydrogen which is making from steam reforming, but which is let me say purified or handled with some treatment in order to remove the CO2 coming from the steam reforming process by treatments and CO2 removal sections. With respect to the water electrolysis, we can separate between several kind of electrolysis. The most important is alkaline electrolysis as well as a PEM, so-called PEM electrolysis there. This means hydrogen can act multifunctional. Hydrogen can act to distribute energy. It can act as a kind of buffer to increase the system resilience. It can help to decarbonize transport with respect to fuel cells. It can used at an energy itself in the industry. It can be used as a feedstock for all the power to X pathways, and it helps to decarbonize building heating, because it can be directly used as a heating material. So I've just said advanced fuels and chemicals. Only a very short explanation what the meaning is of advanced fuels and chemicals. If you look at the biofuels and the biorefinery classification, we see that the biofuels can be distributed into 4 generations: the first, the second, third, and fourth generation. We are just or currently in the 2nd generation fuels. This means that we can produce products from biogenic sources, not from eatable plants, because we have not the problem with eatable material. And we are looking for 3rd generation, where we have biofuels which are able to trap CO2 from the atmosphere, and also for the 4th generation. But just know we are in the 2nd generation. We have to use some production routes, some value chains like biochemical, chemical conversions, and all other listed conversion and production methods and processes. And on the other side, we are able to get from the bio sources energy. We get all liquid products, transport as building blocks, and we can also gain from it all gaseous products. This is the biofuels. If you look at the advanced fuels with respect to synthetic products are starting with the syngas. We need a syngas production. This syngas production can be done with solid liquids or gaseous feedstocks, which are at all not very sustainable, because if we make it from coal or from oil, you know that that's not the way we are going to. But if we use biomass gasification or we use waste gasification, it should be a kind of sustainable building pathway. Or, and that's at the left side, at the button there, we can use new and advanced resources like CO2 reforming, water electrolyzers, or hybrid systems using electrolyzers with biomass gasification. The synthesis gas coming from this production route is essential with respect to the hydrogen to CO ratio, and this is different for the different production routes. So we have some adjustment syngas condition purification steps in order to adjust the hydrogen to CO ratio. And you see at the right side, the adjusted ratio can be used for all downstream processing, like for alcohols, for fuels and oxo alcohols, and as well as for methanization steps, and so on and so on. This means that if we use advanced fuels and chemicals, the so-called power to X fuels, we see that
Thomas, we apologize. Unfortunately, it is very interesting technical presentation you're having, but you have run out of time, and we have still one more presentation. Could we kindly ask you to voice main conclusions, which you have at the end of the presentation, and then if there will be specific questions from the audience, we'll do that during the Q&A session, please. Okay?
Thanks. So let me just say there are a lot of pathways coming out from the power to fuels, which can be done for all products we need. So this means that all the chemicals, that all the transportation fuels can be gained from this new and sustainable feedstocks. So. A very short review in the enhanced process efficiency. I will not go into detail, but process efficiency enhancement means that we have a better energy plus carbon management and control, that we have the ability to benchmark, the ability to calculate the emissions in order to see what is the improvement, what is the current one, and what is the future one. And we have the big area of the circular economy, material cycling, which is shown at the left side, and also the digital expertise, the artificial intelligence, which helps to make the processes more efficiency. Let me give at the end of the lecture some very few examples for technologies areas where thyssenkrupp is involved in. There's a green hydrogen we are very familiar with. Then we have the green methanol as a building block for this components I've just mentioned. We are also involved in many carbon to chemical projects which uses carbon from other industries in order to make new products. And we have the ability for the dedicated decarbonization service, which means all kind of decarbonization excellence for carbon emission benchmarking, green revamps for existing installation, and so on. Let me finalize my lecture with some points. There is a dual change rising the global energy demand on the other side, and the significant reducing of carbon content on the other side. We have a very strong interactions as shown between the refinery, petrochemical, and the chemical industry. There are a lot of proven technologies available and pathways which have to implement it. And by 2050, there will be a mix of sustainable, regenerative, and green energy sources, but also a little kind of crude oil. And during the time beyond 2030, there will be a lot of, let me say, bridging technology or blue technologies, which will have to cover over in the green technology sources. And the refinery will act in 2050 only as a kind of energy hub. So thank you very much. And a very essential message is that we only can challenge this smart solutions for climatic protection if we work cross-industrial networking. Thank you very much.